Now we're going to use the polar coordinates to find the volume of the sphere. Okay, we know from high school that the volume of a sphere is given by 4 pi over 3 r cubed, with r being the radius. So our aim now is to use polar coordinates to find this volume. We know that when we use the double integral to find the volume of the solid, so let's call this one V. So we integrate over some d, some domain, some function that we assume that it is a function of x and y. Okay? In our case, we need to find d and we need to find f. Okay? And we know the equation of the sphere. Okay? And from that, we're gonna get our f here. Okay, so given a sphere that's centered at A, B, C, and having radius r, we can write its equation as x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. In our case, we're gonna take the A, B, and C to be in the origin. That means A, B, and C will be 0. Okay, so there is no difference between finding the volume at some point here and finding it at the origin. Okay, so we're gonna take the A, B, and C to be 0. That means we're gonna take the sphere centered at the origin. Therefore, we have the equation for the sphere as x squared plus y squared plus z squared is equal to r squared. Okay, we can find z. Z squared is r squared minus x squared minus y squared. And if we want to find the square root, we will have to treat two cases. The positive part, or the upper half of the sphere, and the lower part of the sphere. Okay, so remember, when we have a circle and we want to solve for y, we have to treat two cases. We take this one here, the positive part, and the negative part, because this one doesn't define a function. Okay, now for us, we're going to take z, which is going to be the function f of xy, as r squared minus x squared minus y squared. So first, we're going to find just half the volume of the sphere. When we find the half the volume, we gotta multiply that by 2 to get the whole volume of the sphere. Okay, in our case, when we do this integration, we want to integrate over some disk. Okay, in our case here, this is our region. Okay, so this is part of the sphere when z is 0. In this case, we have x squared plus y squared is r squared. And therefore, we can set up this one as our domain or disk. Okay? Here, we can use rectangular coordinates. But for us, we're going to use polar coordinates to make it easy and to see how we can compute the volume in this case using polar coordinates. In this case, the d here, the d is the set of xy in r squared, such that x squared plus y squared is less than r squared. Okay, we can transform this one here as some other d prime, and this one will be in function of r and theta. So here we have r and theta in r squared here, such that r will be between 0 and r, and theta will be between 0 and 2 pi. So this is to cover the whole disk. Okay, and doing so, okay, we have our half volume. Okay, now let's call it half. So let's use h to mean that we are computing half the volume of the sphere. In this case, okay, we're gonna compute the volume over d prime. Okay, And once we do that, we will have the volume over d prime. Our function will be, okay, if we switch to polar coordinates, in this case, x is going to be r cosine theta, and y is going to be r sine theta. This r is less than big R, and theta is between 0 and 2 pi. Okay. Here we have r squared. Let's simplify this function here. So we have r squared, it's constant, minus x squared plus y squared, which is r squared, small r squared. And dx dy is going to be r dr d theta. Okay. Therefore, we can integrate between 0 and 2 pi and 0 and r. Our function here, r squared minus big R squared minus small r squared dr d theta. Okay. Now we see that these two are independent of each other. So we integrate with respect to theta because it's easier. We're going to have 2 pi. And now we have to integrate this one here. Okay. This one we can do a change of variable, or we can see it from here, because if you have enough experience, you can see that this one is, let me move it to here. Let me write it to here. Okay. So if this one here, this integral x, let's call this one r squared minus x squared dx. Okay. It is minus 1/3 r squared minus x squared to the power 3 over 2. Okay, you can check it either you differentiate or use a change of variable. And in this case, the best change of variable that we can do is we let x equal r sine theta. Okay, we know that. Okay, doing so, okay, now we have h, the value of h, this one here, it's going to be 2 pi. So h is going to be 2 pi times minus 1/3 r squared minus small r squared between 0 and, but here I need to have this one, 3/2 between 0 and r. Okay, let me move this one here. So when we have small r squared is equal to big R, we have 0. Okay, and when we have small r is 0, we're gonna have h is 2 pi, and minus with this minus here is gonna give us plus 1/3 times big R squared to the power 3/2, and this will give me 2 pi over 3 times r cubed. Okay, but this is only h is 1/2 the volume. If I multiply h by 2, I will get 2 times 2 pi over 3 times r cubed, and this is the volume that we know, 4 pi over 3 r cubed. Okay, so using polar coordinates, we found the volume for the sphere. Okay, so this is another way that we can use to find the volume. Okay, there are other ways that we can do, but this is an easy way using polar coordinates to do. Okay, thank you very much.